Yep, hello everyone. Thanks for coming. So let's start, and we'll start with a short introduction about what checkpoint restore is. So here in this talk by checkpoint restore, I will mean an ability to take an application running on a Linux machine, to take its state, to snapshot it, to save it in some form on a disk, in the files, so that we can later take these image files and restore the original application in the very same state as it used to be before, at the moment we did a checkpoint. It sounds pretty simple, and this such an ability is a core technology for a variety of usage scenarios. For example, this can be used for applications live migration, when you take an application on one machine, checkpoint it, then copy the files on some other box, restore it there, and it continues running as if nothing has happened, just a small delay in operation. At Parallels, we use this feature for live migration as well. We also use this for so-called bootless kernel upgrade. It's a feature which works like we take applications, well, it's a containers in our case. We take these containers, we save their state, then we change the kernel with the kexec system call, and when a new kernel is up and running, we restore the containers from the initial state. From their point of view, nothing has changed but the kernel, but everything remains intact. It can, in theory, be used for application startup boost. For example, if you have some application which starts up slowly by initializing some internal state caches or similar, you can make this slow startup once, then save a state and restore it from the state on the restart. Similar functionality for virtual machines is used for periodical snapshots of these virtual machines. It will be able to do the same with just Linux processes or containers. And we have not request, but we've seen interest from people working in HPC area that they need this as well for example, load balancing. So it sounds pretty appealing, and you might ask whether it's possible to do all these nice things right now in Linux. And if you ask this, then the answer would be yes, almost yes. We're very close to it, and with this talk I will try to answer the question, how will we be able to do it, how close we are to it, and what has happened since the very first days of the feature. So the roots of the project can be traced back to the 2005 when we first released the OpenWZ project. This project had this checkpoint restore feature from the very beginning. It was the all-in-kernel implementation. It was a big kernel model which did all we need. Later on, when we started submitting our functionality upstream, in several years, we've came to a state when we need to have checkpoint restore upstream, and by that time it turned out there are other parties which are interested in this as well. For example, IBM people were interested in it, people from Mosaics project, and some other guys. So we tried to do it together, doing checkpoint restore as all-in-kernel implementation, and in a couple of more years, a first more or less complete version which could do a lot of stuff was ready, and it was sent for review in the kernel mailing list. It contained over 100 pages, but the community decided that having this huge piece of code in the kernel is not the way to go, as it provides, well, as it leads to various bad things. Quite soon after that, we decided to try doing checkpoint restore in the user space, using the existing kernel APIs to read the state of the applications and to restore it later. However, while doing this, it turned out that some additional support from the kernel is required. We started sending patches, sending sources of the user space tool, and in the beginning of 2012, Linus decided that what additions we need to kernel are worth merging in. He merged the code, and it can be treated as a date of official project start. Soon after that, we released CRIU version 0.1. At the end of the last year, we released CRIU version 0.3, and now we're heading to the 0.4 release. What's our ultimate goal? The ultimate goal of the whole project. Let's consider you have an application. It can have various resources. It's virtual memory, open files, credentials. Typical Linux application has lots of them. There may be more than one application. Several applications can share various things to each other, for example, open files or even memory or many other stuff. These applications can live in an environment known as containers or namespaces or sometimes control groups. So what we want to do is we want to take the whole state of this picture to dump it into some format on a file on a disk, as I told. And this format should contain enough information so that we can later take it and restore the original state exactly as it used to be. To do this, we basically do two core stuff with the project. If I have an application and it requested for a kernel to turn it into some state, for example, it's called an open system call and obtain the file descriptor. In order to dump this particular state, we need to request for a kernel which files are opened by this particular application, or what are the resources this application has, and in which state are these resources, how are they shared, what are the identifiers, and so on and so forth. Later, when we want to restore the state, this task is much simpler, because if this state was somehow achieved by an application, we can use the same API for doing this. So with this, we started looking at what APIs does kernel provide. It can be very roughly divided into three big types of API. It's a proc file system, which provides a lot of information about application state, about its resources, and similar things. It's the whole set of system calls, and which is important. I'll get back to this later. There are two types of system calls. First set of system calls work on a project, on a process itself. For example, opens a file descriptor just for a current process. System call which gets supplementary group IDs, it also works only for the process which is calling it. So we cannot simply use that for fetching a state for arbitrary process. On the other hand, we have a bunch of system calls which work on any process. It accepts a PID value of a process we want to request for example, scheduler policy requesting or IO priority and similar stuff. And there is a subsystem called netlink, which can be used for fetching and restoring back the various networking configuration. We use it widely for network-related stuff. So we took all this API and used proc system calls and netlink for dumping the state, and used system calls and yet again netlink for restoring the state. However, it sometimes turns out that if an application requests for some resource and we're trying to request for a kernel for this resource, kernel cannot provide us this information. For example, there is a set of system calls about POSIX CPU timers. Application can start various timers that will send it the signals in some time. However, kernel does not provide any APIs for requesting what timers are set for a particular application. It doesn't provide any API even for this application itself to request which timers and in which state have I requested. And this happens quite often. So when this happens, what we do is we take this subsystem, think on how kernel API can be extended to provide this information, and submit a patch upstream. Then a regular process of discussing kernel contribution starts. We discuss it with maintainers, sometimes rewrite the code, sometimes redesign it from the scratch, and eventually the thing gets merged. On Restore process, the same thing happens when we try to restore a state in some particular of some particular resource or part of an application. We ask for a kernel to do it, and most likely kernel will, but sometimes it happens that kernel cannot, and typically it happens when we are trying to recreate some IDs in the initial value. For example, if you have a file descriptor, you can restore it at the initial value. There is a DAP2 system call which provides you the necessary facility. But if you want, for example, to create a process with a specified ID, there were no such API before we started this project. Kernel always generated the process ID, and there were no ways to guess what it would be. So what we do in these cases, we do the same. We take the subsystem, patch it, send the patch upstream, and so on and so forth. So the whole CRIU concept was very well described by Andrew Morton. He said that it's a project which is about to perform checkpoint restore mainly from user space, which adds very reusable helper code into the kernel. So instead of one large piece of code in the kernel which does checkpoint restore, we have various bits and pieces popping up here and there in the kernel, helping the guys doing their work. So far, the kernel impact of the project looks like this. We have submitted, and this has been merged, 130 patches, something about this. Within these patches, the kernel gained 11 new features. I will shortly glance through them quite soon. And which is very important is that only one of these features was submitted by us for checkpoint restore purpose only, which means that when submitting it, we had no idea how to use this particular feature outside of the checkpoint restore feature, outside of the checkpoint restore project. All the other features are project independent. It can be used by other tools, other projects for other purposes. So the most interesting features which were created for the kernel. The first feature is an extension of the existing ptrace API. It was developed not by us. It was developed by Tej and Heo. But it was developed for the same purpose. He wanted to do TCP connection hijacking for some of his HPC stuff. So what this feature is about, this thing allows you to transparently trap a process and do common debugging stuff on it, but in a way that it doesn't even notice that anything happens. This patch was pretty short. What it mostly did was technical and dealt with corner cases like a task was stopped or about to handle a signal or about to leave a signal handler or something like that. So with this feature merged, we'll gain an ability to take a process, trap it with a debugger, then inject it to it an arbitrary blob, and then force it jump into that code and execute it. This feature was called parasite code injection. This feature allowed us to use the whole set of system calls which worked on a calling process only. So we've gained the ability to call system calls that, for example, fetch SIG handler state with SIG action system call, to fetch supplementary group IDs, to fetch IO priority and, IO priority. Well, to fetch stuff which otherwise could be only requested by a calling process. This feature allowed us to do it. So we didn't have to invent a lot of APIs extensions. Another feature is the so-called KCMP system call. It's a system call which tells you, it takes two processes. It takes objects which are used by this process, for example, memory, virtual memory or open file or file system view, and it tells you whether the object used by these two processes are equal or the first one is above the second or it's vice versa. It sounds pretty strange, but this system call is used by us to determine how objects are shared between the process. What we do is we just compare process pair by pair and sort the results, so we can see which objects and between which processes are shared. Before this system call, it was impossible to distinguish situation, for example, when the process opened the file, then did a fork. In that case, the file was shared between the parent and the child. It was impossible to detect this before the system call was merged. Another big feature that got merged through David Miller's networking tree is a so-called socket diagnostic subsystem. It's a netlink-based subsystem which dumps into a user space through a netlink socket very complete information about all the sockets in the system. For example, you can request for the SOCDIAG subsystem about which Unix sockets exist in the system. Please tell me. It will dump you a big blob in a netlink attributes format. It's a tree format. So you will find out lots of stuff about netlink sockets. So it can work on UDP sockets, on TCP sockets. Before this subsystem was merged, it was extremely hard to extend the existing interfaces of the kernel to get more information about sockets. For example, if you take two Unix sockets, they can be interconnected to each other. Existing proc Unix file does not contain this information at all, which sockets is connected to which. And adding a new field in this file was impossible because it might break existing parsers. Adding a new file would be not an option because if we want to know more information, we would have to add a third file, the fourth, and so on and so forth. With this netlink extension, it's possible to extend this information easily because netlink attributes format allows extending without breaking existing readers. So with this feature merged and with a patch accepted by Steven into IP route to tool, it's now possible to run SS tool from the command line and find out which Unix sockets are connected to each other. It was not possible before this feature. Sorry. And another very interesting feature of CRIU is so-called TCP repair mode. One of the goals of the CRIU project is an ability to take one end of a TCP connection to save its state and to restore it later somewhere so that the other end of the TCP connection that might be even on another machine doesn't notice this happens. It is used for checkpoint restore, of course, and it can be used for sockets failover. In particular, HP guys came to us after this feature was merged and discussed the details of it. The idea of the TCP repair mode is very simple. We call a socket option system call and tell to a TCP socket that it's turned into a repair mode. Turning a socket into a repair mode means that it will no longer send any packets to a network, and it will react on any system call which changes socket state immediately without performing any protocol-specific communications. For example, if you take a closed TCP socket, put it into repair mode, then call connect, it will immediately turn into established state with the peer credentials set as provided by the sockadder argument. It will not send a SYN request, it will not wait for acknowledgements, it will do nothing, it will be just turn into that state. Or if you will close this socket, it will be closed immediately, like if you set the linger time to 0. This mode is not yet complete. It doesn't support various things like TCP timestamps and similar stuff. But what can you already do with it is save the socket state, close it, and then restore it on the same machine, unfortunately. But we are working on making it work on the generic socket. Other less interesting features, but still include extension of proc-pid FD info files. These files contain various information about file descriptors opened by process. So far, they have contained only file position and flags with which it was opened. Right now, in this file, there might be more information. In particular, for checkpoint restore, we extended several non-POSIX file engines to provide more information. In particular, it's iNotify, SignalFD, ePOL, and EventFD files. They have a very huge internal state. For example, eventfd has a counter, inotify has watches on inodes, and so on and so forth. So these are the info files. If the respective file is one of these, it will contain more information about the state. Another feature is map files directory in procpid subdirectory. It was introduced to help us dumping process mappings. The problem we were trying to solve was if a process maps a memory with a map system call, kernel doesn't provide us enough information about this mapping. Yes, there is a procpid maps file and smaps file, but it doesn't contain two very important things. First, it doesn't contain any information about which mappings are shared with which. You can have shared mappings between different processes, but neither maps file nor smaps file will tell you about this. Another problem is that a file path sitting in the procpid map files is not a reliable identifier of a file. It's a path to a file that the process used to map when it mapped it. Since that time, things might have changed, mount points might have changed, some parts, I don't know, symlinks maybe reset and so on and so forth. So the path you see in map files, in maps files, might not be the file that is really mapped. So what we did is introduce a map files directory. It contains the symlinks on the files which are really mapped. And this symlinks works the same way as the procpid directory. You can open the symlink. It will open you the original file, even if it was overmounted or path changed or whatever it is. And then, having a local file descriptor, you can reliably find out what the file mapped is. Plus, with these symlinks, we can compare the original files, and if they match, this means that the mappings are shared between each other. Yet another feature in the networking subsystem is the socket picking offset. Right now, with the receive message system call, you can pick a message from a queue without removing it from there, but this picking will perform on the very first message in the queue. If you have, for example, UDP sockets with, I don't know, more than 2 packets, you cannot pick the second or the third packet. So what we did is introduced a socket option which allows you to say which message to pick. What we also did is we looked through this, all the socket options that were able, that the process was able to set, but wasn't able to get the value back. For example, the device the socket is bound to, or the packet filter state. And we made these socket options readable as well. With this support from the kernel, the user space tool can right now do the following. It works on x86 64-bit platform and ARM. It supports arbitrary process tree with threads. It supports memory mapping of all kinds, shared private file mappings, anonymous mappings. It supports process groups, sessions, and terminals, so you can dump, for example, a screen with tasks hanging around. It supports process credentials. It supports open files and including files that are shared between processes or that were opened and then unlinked. It was quite a typical scenario for various daemons. It supports TCP, UDP, and Unix sockets. It supports basically established TCP connection. You can dump one end of the connection, then restore it back. And it contains support for LXC container environment. And what's really great about this all is all I've described above already works on the upstream kernel version 3.7. You don't need to compile a custom kernel. You can just clone the Linux tree, put some config options on, for example, this socket diagnostic subsystem. And that's it. The checkpoint restore tool will just work on it. And in version 3.8, already at Linux 3, there sits the fdinfo files extensions. So once the 3.8 is out, you will be able to work with non-POSIX files such as inotify, signalfd, and similar stuff. In order to make sure it works, we use two ways of testing it. First of all, we have a big set of unit tests. It's called ZDTM. It's an acronym from Zero Downtime Migration. It's a set of atomic tests. Each of the tests doing some small thing. For example, one test opens a file, the other test maps an anonymous memory, the third test forks a child, the fourth creates a zombie, and so on and so forth. So we run on this test, then each of them says, okay, I'm ready, try to checkpoint me. We checkpoint this test, then we restore them back and ask for the test, has anything changed from your point of view? And after that, each test checks whether the file is still open, whether the mapping is still in place, whether the zombie still exists, and every test does what it's supposed to. It's very useful for actually for regression testing. And to find out new things to support first, we from time to time take some real software and check whether CRIU tool can work on them. So far we have tested Apache, MySQL, we've tested kernel compilation in 8 threads with Make and GCC, we've checked charring the kernel source tree, we've checked SSHD with connection to make sure that TCP connection repair mode really works, at least on one machine. We've checked screen with top and other tasks running inside to check terminals, because terminals are very tricky. We've checked VNC's server with screensaver and the client connected to it. So client saw that the animation stopped for a while we did a checkpoint and restore and then resumed without any interaction. We checked Nginx with MongoDB under some Mongo benchmark load on it, and we have recently checked an Oracle server to survive checkpoint and restore cycle, but it required quite interesting kernel tweak, so it's not yet in the official repository. Now a few words about integration. The project is currently it's mostly developed by Parallels as a sub-project of the OpenVZ. We have plans to release OpenVZ with CRIU integration quite soon, so that the CRIU will be the main checkpoint restore engine for OpenVZ, not the kernel version we currently have. We have people from Huawei came to us some time ago telling that we want to use the project, but it lacks support for file logs, so here are the patches, so we had contributor. The user space tool now sits in the request queue to be included in Fedora 19, and it sits in Debian Unstable repository to be included into the distribution sometime soon. Our nearest plan include, of course, growing the community, because there are lots of things to do and quite a few people to do all of this stuff. We want also to make full Linux kernel resources coverage. There are more things to be supported, in particular POSIX timers. CRIU currently cannot even detect they exist, and don't dump the process, so it might break later. As I told, there is no kernel API for doing so. We have plans to properly integrate the checkpoint restore tools with the LXC project and OpenVZ project, and the latter things is about to happen quite soon. And another big development feature we're going to make is implementing the kernel support for users for user memory snapshot. It's an ability to tell the kernel, notice process and tell me which pages will it change since this moment. This is a very useful feature that can speed various things up. For example, for live migration, we can first dump the process memory, then copy it to the destination node, but not without stopping the process while doing this, so they continue operating. Then we freeze them and ask for kernel for changes only. This will reduce the downtime significantly. We've seen this in the OpenVZ. It reduces it up to 10 times. Another application of this memory snapshot is if you want to take periodical snapshots of your, for example, HPC calculation task. Currently, what you can do is only take full dumps every time, but it might take very long time if application uses very small working set. If you got interested in, I hope, you might consider visiting these resources. We have a site, CRIU.org, that's the main entry point. There are project news and documentation reside. The user space tool is an open source tool. It's sitting in a Git repository at git.criu.org. Also, CRIU mostly works on the mainstream kernel. However, there are some things which require some additional kernel patching. All these patches we need are sent to the respective mailing lists right at once, so we do not actively developing anything out of the upstream kernel. However, to make testing and usage of this thing easier, we always put these patches into our kernel on GitHub. So if you want some additional features, you might consider cloning this tree and compiling the kernel. Right now, it contains like 10 additional patches for various things. We have a Google Plus page. It's plus CRIU. We have a mailing list, criu@openvz.org. And my email, if you want to talk to me, it's on the beginning. That's all I have. Thank you. If you have any questions.